Hello, this work is titled FD2, a dedicated framework for fine-grained dataset distillation. Dataset distillation compresses a large training set into a very small synthetic set. Our goal is to make decoupled distillation work better on fine-grained tasks by suppressing fine-grained characteristics and preserving same-class diversity. I will briefly present the problem, our two constraints, and the main results. Fine-grained recognition is difficult because classes differ in small local details, while samples within one class vary in pose, viewpoint, and background. Existing decoupled methods mainly use coarse class label supervision. We observed two failures. First, the distilled set inherits large intraclass variance and small interclass distances. Second, samples from the same class converge to nearly identical attention regions. The left analysis shows the unfavorable fine-grained characteristics, and the right heat maps show attention similarity. As a result, the student receives fewer complementary cues for distinguishing similar categories. FD2 keeps the standard three-stage decoupled pipeline. During model pre-training, a backbone and CAL module localize discriminative regions and update class prototypes. During distillation, the frozen teacher processes a group of same-class synthetic images and returns both representations and attention maps. We retain the original distillation loss and add a classification loss plus two new terms, a fine-grained characteristic constraint, LF, and a similarity constraint, LS. After image optimization, the usual soft label generation stage remains unchanged. Because FD2 is an add-on, it can be integrated into SRE2L++ and FAD-RM+, without redesigning their workflow. For fine-grained characteristic constraint, we fuse backbone features with localized attention to build a fine-grained representation for the current distilled image. LF pulls this representation toward its target class prototype and pushes it away from other class prototypes. This improves intra-class compactness and interclass separability. In the TSNE plot, the orange FD2 samples form tighter groups around their centers. This center distance plot also shows larger margins between neighboring classes across most cub categories. The distilled set, therefore, becomes easier for a student to separate. The second constraint addresses within-class homogenization. Samples synthesized in sequence under similar supervision tend to attend to the same object part. We group same-class samples and compare the current attention map with the maps of previous samples. The similarity loss penalizes excessive overlap and encourages complementary regions. In this example, attention shifts across the head, wing, and body of the bird. Mean pairwise cosine similarity decreases from 0.77 to 0.63. The synthetic set therefore carries richer localized evidence within each class. We evaluate FD2 on CU B2002011 FGVC aircraft, Stanford cars, ImageNeta, and ImageWoof. This chart shows a comparison using ARESNet 18 student, 3 images per class, and the SRE2L++ baseline. FD2 improves cub accuracy from 60.0 to 64.9. Aircraft from 66.6 to 76.1, and cars from 68.2 to 75.2. The gains are 4.9, 9.5, and 7.0 percentage points. Across the full study, the largest SRE2L++ gain is 15.1 points on Stanford cars with ResNet 50, and 1 image per class. FAD-RM Plus also improves by as much as 13.8 points. FD-NE improves most general DASA settings and most cross-architecture students. A few small student settings on general datasets show limited gains, which is consistent with the method's focus on fine-grained cues. To conclude, fine-grained dataset distillation needs more than label-level matching. FD2 adds attention-based fine-grained supervision to the pipeline. The LF builds compact and well-separated class structure, while the LS preserves diversity among same-class samples. Together, they produce synthetic images with clearer local structure and improve recognition across fine-grained datasets without changing the underlying distillation workflow. Thank you.